This is CS50, and this is lecture 3. And today, the goal is to be a lot more algorithmic than code-oriented, and to really kind of come back to where we started in lecture 0 when we talked about computational thinking and algorithms, because now you have a few weeks under your belt, and you have a few new tools and hopefully skills under your belt, even though odds are you're still getting comfortable with some of those skills. And so let's look then at this piece of hardware that we've talked about a couple of times, and this is an example of what? Yeah, memory, or RAM, random access memory. And this happens to be pretty big on the screen, but it's actually pretty small if you were to find it in your Mac or PC, in your laptop, or some other device. And this is just memory. And so memory is places you can store information, numbers and characters and strings and bigger things still. And recall that if you want to use this memory, you need to address it. You need to put something in particular locations, and we're going to start doing this all the more. So in particular, there's at least like 4 black chips on here, which is actually where the zeros and ones are stored, and the green circuit board and the little gold connectors you see on the screen too. That just allows all of those black chips to intercommunicate ultimately, and for the zeros and ones to move around. But if we zoom in on just one of these chips of memory arbitrarily, and then zoom in here, you can think of this, wonderfully enough, as like a rectangle. Could be any shape, certainly. But if we think about it as a rectangle, we can divide this chip of memory up into like a grid like this. Completely arbitrary how I've drawn this. But the fact now that I have a whole bunch of small boxes, you can start to think of this as being 1 byte, and then another byte, and then another byte. And I coincidentally wrote 8 bytes across, but it could be any number. It doesn't really matter. And so you can start to think about these bytes as having specific locations or numbers or addresses, as we're going to start calling them. So if I zoom in on the top of this, you could start to think of the top left as being byte number 0, because computer scientists generally start counting at 0, and then byte 1 and 2 and 3 and 4 and dot, dot, dot. And then just as a refresher, in a typical Mac or PC these days, like how much RAM or memory would you typically have? 4 what? 4 gigabytes, and giga means billion, so that's 4 billion bytes. And maybe you have a little less, maybe you have a little more, but on the order of billions of bytes. So we're only scratching the surface of just how much storage there is and how many numbers and characters you can store. But the point is that we can address them in some way, 0, 1, 2, and so forth. So this is how we stored Stelios's name in memory. Recall this was an example last time where we needed to put the characters of his name somewhere. And so we actually put the S and then the T and then so forth, starting at the leftmost location on forward. But we also put something else. It's not sufficient just to put the letters of his name in memory. What else did we have to do? Yeah, the 0 command, or more specifically, the 0 byte, or the so-called null byte, NUL, and it's represented as \0. Because if you were just to type a normal 0, that would technically be a character from your keyboard. It looks like a number, but it's technically a character, a char. And so \0 literally means 8 0 bits in that byte's location. OK, so now that we had this ability to represent Stelios with a sequence of characters, null terminated at the end, we don't really need to worry about the hardware anymore, right? We can abstract away from that, just as we did in week 0, and not worry about how those zeros and ones are stored. We can just trust that they are somehow. And so we can abstract away and just start thinking about it as a sequence or a grid of letters like this. But that \0 is important, because it is the only way that this language we're currently using, C, knows where strings end. If you didn't have that, it would, printf, for instance, might just keep printing all of the contents, all 4 gigabytes of memory that your computer has, no matter what those characters actually are. And then, of course, you couldn't distinguish Stelios's name from Maria or someone else altogether in memory. So let me go ahead and open up the IDE just to demonstrate now what you can do with this kind of knowledge. Suppose I wanted to write a program that allows me to let a user type in his or her name, and then I just want to print out his or her initials. And for simplicity, I'm going to assume that the person's initials are whatever the capitalized letters are in the input they type. So I have to be a little nitpicky and type in my name properly. But with that said, let me go ahead and whip this up. So I'm going to save this as initials.c. Just out of habit, I'm going to start by including the CS50 library, because I'm going to want to get a string from the user. I'm going to go ahead and include standard io.h so that I can print something to the screen. And we'll decide later if we need anything more. I don't need any command line arguments for the purpose of this program. So I'm going to go back to our old version of main, where you just specify void, no argc, no argv. And then here, let me go ahead and declare a string called s and get a name from the user, as with quote unquote name and get string. And then what do I want to do after this? I want to go ahead and iterate over the characters in the user's name and print them out only if they're uppercase. But you know what? Rather than just print them out, you know what I want to do? I actually want to create a new string myself containing the user's initials. So I don't want to go ahead and just print out with %C one character after the other. Rather, I want to go ahead and store the user's actual initials in a new string so that I've got one string for their name and one string for their initials. And ladies and gentlemen, Ian. Sorry for the video glitches. Thanks. All right, so to be ever more clear, let me go ahead and rename this to name literally. And then I want to have a string for their initials. But we know what a string is as of last time. It's really just a sequence of characters. And a sequence is really has another name in programming. What is another synonym we've used for a sequence of something? An array. An array is that data structure we had when we started using square bracket notation. So if I actually kind of roll this back and break the abstraction, if you will, don't think about it as a string. What is a string? It's a sequence of characters. Technically, I could say char, and then I could say initials, and then I can specify however many letters I want to support in a human's initials. And by assuming we have a first name, maybe a middle name, and a last name, 3 characters should do it. 3 characters. So David J. Malan, like DJM, 3 characters. Is that enough chars? I'm hesitating because it's not, but why?
You need for the null character.
Yeah, so if we want to terminate even my initials, which isn't technically a word, but it's certainly a string, a sequence of characters, we need a 4th character, or we need to anticipate a 4th character so that whatever we put in the computer's memory is technically, in my case, like DJM \0. You need that 4th byte. Otherwise, you do not have room to actually terminate this string. So now, even though this doesn't look like a string insofar as I'm not saying the word string, it really is. It's a sequence of characters of size 4 that I can put characters in. Now, what are the characters in this array by default, have we said? When you just declare a variable of some size, what values go in it? Sometimes zeros. But generally, what's the better rule of thumb? Yeah, you don't know. It's so-called garbage values. Nothing, you should not trust the value of a variable, generally speaking, unless you yourself have put the value there, or as by storing it with the assignment operator, or by manually typing it in yourself. So just to be clear, if I wanted this program to be kind of useless for anyone except myself, I could actually do this. I could go ahead and do initials bracket 0 gets quote unquote D. Initials bracket 1 initials bracket 1 gets quote unquote J. And then finally initials bracket 2 gets quote unquote M. And then lastly, and this is the thing you might forget sometimes, you actually need to do the /0 there. But of course, this is not at all dynamic. But I have in these lines of code now created a new string called initials. It's of human length 3, DJM, but the computer is actually using 4 bytes to store it. But this is not the point of the exercise, because we already asked the user for his or her name. I need to now figure what that is. So just logically, or algorithmically, if you will, what process could we use, given a name like David J. Malan, or Brian Yu, or anyone else's name, how could we look at that input and figure out what the user's initials are? What's the thought process? Let me go a little farther back. So David J. Malan, or any other name. What's the process? What do you think?
You could use a for loop to iterate through the characters in the name.
OK.
To
OK, good. So iterate with a for loop over the letters in the name. And you've done that before, or in the process of doing that for something like Caesar, Visionaire most likely. And then you can use something like isUpper. Or you can even do ASCII math like we did a while ago to actually determine, is it in the range of A to Z capitals on both ends? So we have a couple of options. So let me try to convert that to code. Let me get rid of the hard-coded name, which is just kind of nonsensical, but demonstrative of how we could store arbitrary characters. And now let me do this. For int I gets 0, I is less than the string length of name, I++. And then I'm going to do something like this. If the ith character in name is an uppercase letter, and I'm going to use a function that you might not have used yourself, but recall that it does exist. IsUpper will return essentially true or false. This is an uppercase letter. So if this is uppercase, I'm going to go ahead and do what? Well, the story is not quite complete. It's not enough to just iterate over the names and the letters in the name. We now need to decide where to put the first capitalized letter that we find. It's obviously going to go in the initials array. But what more do I need to add to my code to know where in this block of 4 characters to put the first character D in the case of my name? Yeah? Initials I. OK, so if I do that, good thought. So let's do initials bracket I gets name bracket I. That would seem to put the ith character of name at the ith location in initials, which at the moment is perfectly correct because I is 0. And if I typed in David J. Malan, D is at the 0th location. So we're good. But there's going to be a bug here. Exactly. I is going to continue marching forward 1 character at a time through the entire name of the user, but you only want to index to, you don't want to keep doing that same amount in the initials array, because again, the initials is much smaller. So even as I moves through the user's name, you want to take baby steps, so to speak, through the initials. So how can we solve this? I can't use I, it would seem. OK, great. Let's do that. We need another variable. So I could put this in a few different places, but I'm going to go ahead and put it here for now. So int counter gets 0. I'm just initializing my counter to 0. And then as soon as I find an uppercase letter, I think I want to do this. Put it at whatever the value of counter is. And then there's one more step. What do I need to do once I, put it at the counter location? Exactly. Increment counter by 1. So I can do this in a few ways. I can do it very literally. Counter gets counter plus 1, semicolon. It's a little annoying to type. You could do plus equals 1, which is slightly more succinct. Or the ever prettier plus plus, which achieves the same result. Fewer characters, same exact result in this case. OK, so now I think we have a for loop that iterates over all of the letters in the name. If it's an uppercase letter, it stores that letter and only that letter in the initials array, and then increments counter so that the next letter is going to go at the next location in the initials array. So if all that seems to be correct, ultimately I want to do this. I want to go ahead and print out %s \n initials. I want to just print the user's initials, but there's one key step in this blank line that I should not forget. What's the very last thing I need to do? Yeah? Exactly. I need to put a null character at the end of the array. So how do I do that? Well, I have the syntax, and I think, I want to say end of array. But how can I do that? What value should I put here? Yeah? Yeah, I could do str length of name. Well, not of name. The initials, but now you kind of got me in a circular argument because I'm trying to, it's kind of a catch-22 now. I am trying to store a \n at the end of the string, but recall from last time, the way strlen knows where the end of the string is by putting the \0. So it's not there yet. So we can't use strlen, but we already have, I think, the solution. OK, so we could absolutely do that or almost that. It's not quite 4. One tweak here, yeah? In back, yeah. OK, good. So actually, so counter is, spoiler, counter is going to be the answer. But let me just fix this one bug here. 4 was the right intuition. But remember, if you have 4 characters possible, it's 0, 1, 2, 3 is the very last one. So we needed to fix that to 3. But even more general would be to put counter, because the value of counter is literally the length of the string we just read into the initials. And so if we want to terminate that string, we already know how many characters we've counted up. And in fact, it would technically be wrong to just blindly put \0 only at the very end of these 4 characters. Why? In what situation would that be logically incorrect? Yeah? If they have more than 3 initials, we really have a problem because we don't have space for anything beyond 3 actual letters and a null terminator. And there's another problem potentially. Yeah? Yeah, if they don't have a middle name, there's going to be only maybe 2 letters, first name and last name. And so you're putting the \0 at the end of your array, which is good. But what's going to be that third value, that second to last value in the array? it's just garbage, so to speak. And so it could be some funky character. You might get weird symbols on the screen. You don't know because it's just incorrect. The \0 has to go at the very end of the string. So let me go ahead, and if I've made no syntax errors here, let me go ahead now and save this and go ahead and do make initials. OK, so implicitly declaring library function strling with type unsigned long. So there's a lot of words, only some of which I kind of recognize immediately. I could run this through help50, which should be your first instinct on your own or in office hours. But let's see if we can't tease apart what the error actually is. What did I forget to do? Yeah. Yeah, I've needed the string library, which now I'll start to get into the habit of more. Anytime I'm using strling, just try to remember to use string. Otherwise, you'll see that error message again and again. Maybe there's more errors, but I'm not sure. So I'm going to go ahead and just recompile. Because again, you might have more errors on the screen than you actually have in reality. But there is indeed one more. So similar error, but different function. Implicit declaration of function is upper. So that's, again, same mistake. I've forgotten something. Anyone recall? This one's a little more less common, I would say. Yeah?
You need the character type library.
Yeah, the character type or C-type library. So again, you'd only know this by checking the man page, so to speak, or reference.cs50.net, or checking your notes or whatnot, or Google. And so that's fine. It happens to be in ctype.h. Now, let me go ahead and recompile. Seems to work. So initials, let me go ahead now and type David J. Malan, enter. Seems to work. Let me try a corner case like Rob Bowden without his middle name, RB, and so it seems to work. This is not a rigorous testing process, but let's trust that we did at least get the fundamentals right. But the key here is that we broke this abstraction, so to speak, of what a string is, because if you understand that, well, a string is just a sequence of characters, and hey, a string must end with a \0, you can do that yourself. And this is what you can do in C. You can put characters anywhere you want in memory. You can put numbers anywhere you want in memory. And this ultimately gives you a lot of power and flexibility, but also, as you'll soon see, a lot of opportunities for bugs with this power. All right, any questions on that particular example? Yeah?
Can you explain the initials counter?
Sure. Sure, let's explain the initials counter, which is used here and is declared up here. So we essentially want to keep track of two locations. If my name is sort of this length, I'm going to start at the first character, D, and with I, iterate from D, A, V, I, D, space, and so forth. So that one just kind of marches on one step at a time. The initials array, meanwhile, is another chunk of memory. It's of size 4, somewhere else in that green silicon chip with all those black chips on it. And we want to move through it more slowly, because we only want to move to the next location in the initials array once we've put a capital letter in it. And that's going to be less frequent, presumably, unless the user typed in all caps. So in order to achieve that, we need a second variable. And you proposed that we use a variable called counter, but we could have called it j or something else. And so counter is initialized to 0, and it is incremented here anytime we encounter a capital letter. So it has the effect of literally counting the capital letters in someone's name, D, J, M. So it should be 3 at the end of those loops. And that's perfect because, as we realized earlier, 3 happens to be the correct location for where you put the \0. Even though it wants to go in the 4th location, the address of it, or the location, is technically 3. So we sort of solve multiple problems at once in this way. Good question. Other questions? Other questions? All right. So with that said, let's not worry as much about that low-level kind of implementation and consider what more we can do with these things called arrays. If we start to get rid of the addresses and just know that we have sequence of characters or anything else in memory, and really at the end of the day, we have the ability to lay things out contiguously in memory, back to back to back to back, like this. So here are then 8 boxes inside of which we can put anything. But we've kind of been cheating as humans for some time. When we had Stelios' name on the screen, all of us in this room just kind of glance up, and you kind of absorb his name all in one fell swoop. But it turns out the computers are not quite as intuitive or as all-seeing as we are, where we can sort of take in the whole room visually. A computer can only look at one thing at a time. And so a better metaphor than a box like this for the locations that you have in your computer's memory would really be like 8 lockers in a school, where a computer, in order to look at the value in any of those boxes, actually has to do a bit of work and open the door to see what's inside. And you cannot, therefore, see all 8 locations simultaneously. So this is going to have very real world implications, because now if we want to start checking the length of a string or counting the number of things in an array or moving things around, we're going to have to do one thing at a time. Whereas we humans might just kind of look at it and say, oh, sort these numbers in some intuitive way. And that actually is a good segue to a very different problem, which is that of sorting values. So for this, we have, say, the equivalent of 7 lockers up here now. And behind these doors, so to speak, is a whole bunch of numbers. So we'll transition away from characters and strings and just generalize it to numbers, because they're convenient to work with. And we have so many of them at our disposal. But I'd like to find one number in particular. So suppose that a computer, we're storing an array of numbers, a whole bunch of integers, back to back to back to back. Here's what they might look like. The doors are closed, though, so we need an algorithm for finding a number. Because the computer can't just look at it and say, there's your number there. The computer has to be more methodical, probably going from left to right, from right to left, starting in the middle, randomly opening them. We need an algorithm. So for that, can we get one brave volunteer? Yeah, OK, come on down. What's your name? Kristen? Chrissy, come on down over this way. All right, so Chrissy, all you know is that there are 7 doors. Nice to meet you. Here on the screen. And using your finger, you should be able to just touch a door to open or unlock it, and we'll see what it is. And I would like you to find the number 50. Damn it. Okay, very good. I feel like we need a better prize than a stress ball for that, but very nicely done. And let me ask you, if we can, if you don't mind me putting the mic in your hand. Here you go. So what was your amazing algorithm for finding 50?
I just clicked on it.
OK, that's
it
great.
Nice.
OK, so good. So wonderfully effective. Let me go ahead and reveal. Actually, let's do this. So here's where you could have gone wrong. Any number of places. And let me ask the audience before we try one other example, what strikes you about these numbers? Anything in particular? They're all in order? Unordered, kind of random. Although the very astute might notice something. Or someone who watches too much TV. Yeah? Yes, thank you. The 2 of us watch a lot of Lost. So plus we had to add a 7th number, so we added ours. So they are actually in random orders. I just kind of shuffled them arbitrarily. They're not sorted from smallest to biggest. They're not sorted from biggest to smallest. There's really no pattern, because I really just did shuffle them up. And that's problematic, because even though Chrissy got lucky finding 50, or was just so good at finding 50, it might be hard to replicate that algorithm and find it every time unless you know a little something about the numbers behind the doors. And so we do know that in this next example. So in this next example, there are still 7 doors and still the same 7 numbers, but now they're sorted. And knowing that, does that change your approach?
Well, I guess if they're sorted like lowest to highest, then it would, because I would know it's closer to the end. But if I don't know how it's sorted, then I guess I wouldn't really know.
OK, good. So let me stipulate they're sorted from smallest to biggest. And let me propose that you again find us the number 50. Yeah, this is not working out very well. OK, that is very well done. OK, so congratulations. One sec. So you'll see, thank you. So you'll see just how much more efficient her second algorithm was when she leveraged that information. But in all seriousness, you could do better, especially for very large data sets, if you know something about the data. If you know that these numbers are sorted, you could, as Chrissy did very intuitively and very correctly, go to the very end knowing that that's the biggest number. It's probably all the way on the right. If she didn't know that, and just knew that the numbers were sorted, and did not know if 50 was a small number, a medium number, the largest number, just it was a number behind doors, what would a smart strategy be, given that lesser information? Yeah, we can try that same divide and conquer approach we did in the very first class with the phone book, right, where we looked roughly in the middle, because we know that the M's, give or take, would be in the middle. And then if we're looking for Mike Smith, whose name starts with an S, we know that he would be to the right. And so we would go to the right and then divide the problem in Today is not going very well. We would divide and conquer the problem again and again. And we can do that here. Even though it's not quite as visually engaging as a phone book, you can kind of go to the middle. And if Chrissy had opened that middle door and seen 16, you would know what. And actually, I can recreate this. I'm just going to refresh the screen. So in this case, we have the same doors. I know 50 somewhere. And I don't know where it is, but 16. Now I know it's to the right, as you propose. So now I can essentially eliminate all these doors, not even worry about them. And indeed, if I open them, we can confirm that I don't need to waste any time actually searching them. Now I've got 3 doors. What would you propose we do next? Yeah, go in the middle again. So here, 42 is a great answer, but it's not the one we're looking for. And indeed, we can throw this half of the problem away and finally search the right half, which now has been whittled down to 1. And then we would find 50. And if I can reconstruct what would have been a great history in the first example, how well might Chrissy have done theoretically, or if we did this exercise again and again and again with the first example? If you don't know anything about the numbers, you can get lucky, as one might, by just choosing a door, and wow, that happens to be the number. But that's not going to happen all the time, most likely. And so you might have to just start, maybe at the beginning. No. No, maybe you can get clever and skip ahead. No. OK, eventually, you will find it if it's actually there. But if you don't know anything about the numbers, the best you can do is what's called brute force. Just brute force your way through the possibilities until you find the answer. But in the worst case, how many doors might I have to open to find the number 50 if I knew nothing about them? Yeah, so all 7, right? If n is the number of doors, it might take me as many as n steps. In this case, it was like n minus 1 or 6 steps. But in Chrissy's case, clearly, there's a really exciting lower bound, because if you do get lucky, it might only take you 1 step. So that's an interesting range to consider. The solution to your problem might take 1 step, or n steps, or any number in between. But the binary search that you proposed in the second approach, where you divide and conquer, recall that when we did that in the past, we had a very nice shape to the curve that we drew that described the efficiency of that algorithm. And we'll come back to that before long. But let's just, for clarity, formalize just what these 2 algorithms are. If I start from the left and go right, or start from the right and go left, following a line, we would call that linear search. And it can be written in any number of ways. I came up with this pseudocode. But again, any reasonable person could come up with an alternative one and say it too is linear search. These are not official definitions. And I wrote it as follows. For each element in array, if the element you're looking for return true. So this is a very concise way of saying for each element in the array, just look at it from left to right or right to left. If it's the one you're looking for, return true. I found the number 50, or whatever it actually is. Otherwise, return false at the very end. And notice the indentation. I unindented it, because only as the very, very last step do I return false if none of my iterations through the loop actually return true. So that would be linear search. Binary search, you have to be a little more verbose to explain it, perhaps. And there's many different ways to write this out. But this is very similar in spirit to something we saw before with Mike Smith in the phone book. So if we go ahead and look at the middle of the sorted array, just as you proposed, and if the element you're looking for is right there, go ahead and return true. I found 50. I got lucky. It was dead center in the middle of my array in one particular running of this program. Else, if the element is to the left, search the left half of the array. Else, if it's to the right, search the right half of the array. Otherwise, return false, because it's presumably not there. So this would be binary search. And even though it's more lines of code or pseudocode, it arguably should be a little faster. Right? Because of that dividing and conquering and throwing half of the problem away, the problem gets smaller much, much more quickly. All right. So with that said, it seems to be a very good thing that having things sorted for you is a very powerful ingredient to a problem. Right? It takes more work, should have taken Chrissy more work, would take all of us in general more work to find a number using linear search than by using binary search. Much like it would have taken me forever to find Mike Smith flipping one phone page at a time versus using the divide and conquer, where I found him much more quickly by dividing the problem in half and half and half again. So that invites the question, how do you get something sorted? Well, let me go ahead and pull up these things, which we happen not to use in this class. But elsewhere on campus, you might have these blue books. And at exam time, you might write your name in the class and all that on them. And we've kind of simplified. So this is a person whose last name starts with A. Last name with person's name starts with B. C, and all the way to Z. But suppose that people finish at different times during the exam, and of course, like you're in the science center or wherever, everyone just starts handing them in, and they kind of come in like this, and then the TF's at the front of the room, or professor has to actually sort through these values. Well, what's this algorithm going to be that we actually use? If you've got a pile of exam books like this, all of them have a letter associated with them, how would we go about sorting these? What do I do? Compare two at a time. OK, so let me go ahead and pick up a couple here. And since I'm the only one that can see them, you should be able to see them on the overhead, thanks to Ian and Scully. So P and H. So H goes before P alphabetically. All right, now what do I do? Pick up another two?
Pick up one.
Yeah, so maybe just pick up one. And I happen to get N, so that goes in between H and P, so I can kind of slide it in. Now I picked up G. That goes before H. Now I picked up another one, E. That goes before G. So it's actually getting kind of easy. Uh-oh, U. This goes at the end after P. And so I can keep grabbing one at a time, F in this case, and then kind of insert it into its appropriate location. And we won't do this the whole way, because it's going to get tedious, and eventually I'm going to embarrass myself by getting one of the letters wrong. But that's an algorithm, right? For each book in the pile, pick it up, compare it to all of the elements you're already holding, and insert it into the appropriate location. And we can actually call that something. That's something called insertion sort, insofar as the emphasis of the algorithm is, thank you, on inserting letters, in this case, into their appropriate location. So with that said, are there other ways than that? Let's go ahead here, and we have enough stress balls to do just one more human demo here beyond these books. These numbers here, suppose we wanted to sort these. I have 8 stress balls, 8 pieces of paper. Could we get 8 other volunteers? So yes, right in back, 2, 3, let's go farther back, 4. Can I go farther back? 5, 6, 7, and 8. Come on up. Oh, next time. Next time. All right, come on down. OK, what's your name?
Jerry.
Jerry. All right, great. If you want to go ahead and step in front of a board there.
Armar.
Armar. David.
Chris.
Chris. David. Frankie.
Kaylin.
Kaylin. Nolan. David.
Jay.
David.
Matthew.
David. OK, so this is statistically anomalous insofar as we're actually very excited to say in CS50 this semester, for the first time ever, we watch these numbers annually. We actually have 44% women in CS50 this year. So as you can see, none of my demonstrations are going correctly today, but trust in that data. So if each of you could stand behind one of the music stands here, hopefully I have counted out exactly 8 people. We have in front of you guys numbers. So go ahead and turn around the pieces of paper, which represent the numbers that we have on the board here if I got the same order right. So there's going to be a bunch of different ways we can sort these 8 values. So how do we go about doing this? Well, much like you proposed earlier, just pick up a pair of blue books and compare them. Why don't I try that same intuition? So 4 and 2, these numbers are obviously out of order. So what do I want to go ahead and do? Yeah, so I can go ahead and swap these. And now problem is solved, which is great. I've taken a bite out of the problem. Let me move on. 4 and 7, those look OK. 7 and 5, not OK. So what do I want to do here? Yeah, so I can swap those. Thank you. So 7 and 6, also out of order. Let's swap those. 7 and 8, that's good. 8 and 3, not correct. So if you want to go ahead and swap those. And 8 and 1, if you want to go ahead and swap those. So what was the net effect? Have I sorted this list of numbers? So obviously not, but I did improve it. And what's the most glaring example, perhaps, of the improvement in front of these? Yeah. 8 is now at the very end. So the biggest number, if you will, bubbled up to the end as though it was bigger and sort of bubbled up. So that's good, but there's still work to be done here. So I can, again, just try to fix these problems locally. Just pick up a couple of problems and try to solve it. So 2 and 4, we're good. 4 and 5, 5 and 6, 6 and 7. Ooh, 7 and 3, if you guys want to swap those. Wonderful. And then 7 and 1, we want to do it again. And now do I need to bother comparing 7 and 8? Technically, no, right? Because if we know 8 made its way, now we can start cutting some corners, but correctly, just to shave some time off of the algorithm, make it a little more efficient. Good. So sorted now? No, so we have to keep doing this. And let me let you guys now execute this pairwise at a time. So here we go. 2, 4, 4, 5, 5, 6, 6, 3, 6, 1. And we can stop there because we know 7's in order. Now we do it again. 2 and 4, 4 and 5, 5 and 3, 5 and 1, Improved, good. And now next, 2 and 4, 4 and 3, 4 and 1. And then 2 and 3, 3 and 1. And then 2 and 1. OK, now it's sorted. Yes, very well done, very well done. So it's kind of tedious, frankly, and I didn't want to keep walking back and forth because thankfully we have like all of this manpower, these multiple CPUs, I guess literally today. So we have all of these CPUs or computers that are able to help me out, but it was still very slow. I mean, it's a long story. So let's rewind just once and do one more. If you guys could rearrange your pieces of paper so that it matches the screen again, just to reset to our original location. Let's go back there. And let's try one other approach. I've tried the insertion approach, whereby I just take a problem like the blue book and insert it into its correct location. But honestly, that was getting a little tedious, and that's why I aborted, because it's going to take me longer and longer and longer to find the right location among all of those blue books. So let me try just a more intuitive one. If I want to sort these numbers, let me just go and select the smallest number I see. OK, 4 at the moment is the smallest number I see, so I'm going to grab it for just now. Now, again, these are lockers, even though we humans can see them all. The computer can only see one location at a time, and this is indeed the smallest number I have seen thus far. So I'm going to grab it. Oh, but very quickly, I can abort that because now I found an even smaller number, so I'm going to hang on to that instead. 7, I'm not going to worry about that. 5, 6, 8, 3, 1. I found a smaller number. Now, I need to kind of do something with this. I want to grab the 1, so I could just put the 2 here. And what do I want to do now with the number 1? Yeah, I kind of just want to put it here. And so I can do this in a few different ways. But you know what? I'm just going to evict whoever's here, because it's a pretty low number, but it's also random. It could have been a big number. So let me just make room for it and do that. I have selected the smallest element. Is the list sorted? I mean, obviously not. But is it better? It is, right? Because the 1 is now at least in the right location. So I've solved 1/8 or 1/8 of the problem so far. So that's not bad. What could I do next? Let me apply the same algorithm. Let me select the smallest, which is currently this one, still this one, still this one. Nope, 3 is smaller. Oh, 2 is even smaller. So let me ultimately grab this. And you know what? 4, you really don't need to be there. I'm just going to evict you again and put 2 where it belongs and move this one over here. So now the list is even more sorted. And if I proceed to do this again and again, if you want to just keep handing me the smallest number, 3. OK, so I'm going to go ahead and just evict 7, because it's kind of a random number anyway. And now, thank you, 4. I'm going to go ahead and evict 5. Even though kind of feels like I'm making a little bit of work for myself, on average, it's not going to matter. Sometimes it'll be good. Sometimes it'll be bad. So let me go ahead and put 5 over here. Now I need to select the next smallest element, which happens to be 5. So we recovered pretty quickly, so I'm going to evict 6 over here. Now I'm going to look for the smallest element. Now it's indeed 6. I'm going to evict 8, put this over here. And now 7 is good, 8 is good, done. But it's still kind of a long story, right? Like I'm going back and forth, looking for these numbers. But this would be what we'd call selection sort. So thank you all very much. If you'd like to keep your pieces of paper, you're welcome to. And let me give you, give you guys a stress ball as well, and a round of applause, if we could, for you guys, if you want to hand those out. Thank you. So as before, let's see if we can apply welcome back. Let's see if we can apply some pseudocode to this algorithm, because it's one thing to sort of talk about it, and it's one thing to sort of reason through it intuitively. But at the end of the day, if you want to program this, we've got to be more precise, and we've got to consider the lower level operations that the computer is going to execute. So here's how we might implement bubble sort. Repeat until no swaps. For I from 0 to n minus 2, and n is just the size of the problem, the number of doors, the number of humans, the number of numbers, whatever the input to the problem actually is. So for I from 0 to n minus 2, if the ith and the ith plus 1 elements are out of order, swap them. So this is kind of a mouthful, but if you think about it, I'm just kind of applying some of the vocabulary that we have from C and kind of sort of from scratch to an otherwise very organic human experience, but using more methodical language than I was just kind of doing off the cuff when we were doing it with humans. Because what does this mean? For I from 0 to n minus 2, that means start at like the 0 location. And if there's n elements here, this is 0. And this at the very end is location, it's going to be n minus 1. right? If you start counting at 0, you have to readjust your whole life to subtract 1 from the tail end of those range of numbers, right? Zeros, if that was 1, this would be n. But if that were 0, this is now n minus 1. So I'm saying, though, for I from 0 to n minus 2, which is technically this. So I'm using sort of for loop-like language to start iterating here and do something like this up until the second to last element, which we've not done before. Seems almost buggy. But if you read ahead in the pseudocode, why did I do that? And only iterate until the second to last element with I. What jumps out at you? Yeah?
Because then you're going to swap the I from the I plus 1 element.
Good.
When you get to n minus 2, you'll swap it with n minus 1.
Exactly. Recall that bubble sort was all about swapping, or potentially swapping, pairwise elements, neighbors, if you will. So you have to make sure that if you're iterating through all of these numbers, you have to stop short of the end of the array so that I plus 1 actually refers to an element that's actually in your list, and not, for instance, way over here, which would be some garbage value that you shouldn't actually touch. So if those elements are out of order, we swap them. And I have a big outer loop there that just says keep doing this again and again and again until you don't swap anything, at which point you can infer that you're done. Because every time I walked back and forth on the list and the guys helped out by swapping their numbers as appropriate, I kept doing it again if there was still room for improvement. And intuitively, why is it absolutely logically safe to stop that whole process once you have not made any swaps on a pass through the list? Why is that a safe conclusion? So if I walk through the list, no, these are good, these are good, these are good. OK, you didn't want your number. These are good, these are good. How do I know that I don't need to do that again? It's sorted already, right? It would be kind of irrational if you've walked through the list looking at everything pairwise, found nothing to swap, to even bother doing that again. Why would you expect different results if the numbers themselves are not moving and you didn't move them yourself? So you can just stop. But this still is going to invite the question, well, how expensive was that? How many swaps or comparisons did we make? And we'll come back to that before long. Selection sort, though, can be expressed maybe even a little more succinctly. And that was the second algorithm we did with our 8 volunteers here. For I from 0 to n minus 1. So this time, all the way through the end of the list, find the smallest element between I and n minus 1. So between those two ranges, the beginning of your list and the end. And then swap the smallest with the ith element. So what does this mean? So again, for I from 0 to n minus 1, this is just pseudocode for saying start a variable I at location 0. And do this until I equals n minus 1. So do this until you've gone all the way through the list. What is it telling me to do? Find the smallest element between the ith element and the end of the list. N minus 1 never changes. It always refers to the end of the list. So that's why I walk through the list looking for ultimately the number 1. And what did I do with the number 1? Swap the smallest with the ith element. And I might have gotten one of these steps wrong when I did a little switcheroo, but we fixed it thereafter. Ultimately, I kept evicting whoever was in the ith location to make room for the element that I knew belonged there. And I could have shuffled them to make room for those elements, but it turns out mathematically it's just as fine to just evict it and move it all the way to the end as we did. And once I've gone all the way through the list, there's no more smallest element to find, and as we saw, the list is sorted. So maybe this is faster, maybe this is slower. It's not immediately obvious. An insertion sort, which we actually came up with by way of the blue books on the floor, might be described as this. For I from 1 to n minus 1, call the 0th through I minus 1th elements the sorted side. That's a mouthful. So consider the left of your list the sorted side of the list. And initially, there's nothing there. You have 0 elements sorted to your left and 8 unsorted elements to your right. So that sort of describes this story when we had volunteers and numbers here. There are no elements sorted. Everything to my right was unsorted. That's all that's saying. Remove the ith element. That was like picking up this blue book, if we were using blue books in this example. Then what do I want to do? Insert it into the sorted side in order. So if this is the sorted side, this is the unsorted side, this is the equivalent of saying take that blue book and just put it in the first location. And you can kind of make a visual gap for it. Now this is the sorted side. This is the unsorted side. Or equivalently, when I was down here with the books in my hands were the sorted side, and everything still on the stage was the unsorted side. Same idea. So what happens next? I then iterate one location next, and I remove the next element. And whatever number that is, I figure out, does it go to the left or does it go to the right? which was the same thing, again, on the stage, me sort of picking up a third blue book and deciding, does it go in between these books? Does it go below? Does it go above? I inserted it into its appropriate location. So in this insertion sort algorithm, you sort of take each number as you encounter it and deal with it then and there. You take the number and deal with it. So you know what? This one's got to go here, if we just kind of pretend what the numbers look like for a moment. So that would be inserting it into the right location, like I did with the blue books. Maybe this one, oh, maybe this one's a really small number. And so I insert it over here. So I kind of literally deal with each problem as I encounter it. But it just gets expensive or really annoying to have to like move all of this stuff out of the way to make room for those elements. And that's why I got bored with the blue book example, because it was getting very tedious looking through all of the blue books for the correct location. So in short, all three of these algorithms, while very differently expressed, and while all of them are kind of intuitive until you try to describe what your human intuition has actually been doing for the past some number of years, that you've been sorting things just for in the real world, they can all be described at least in terms of these algorithms. So these algorithms, and we started this conversation in the first lecture, all have ultimately some kind of running time associated with them. Like how long does it take to do something? And we talked about the process of finding Mike Smith in terms of this pretty generic graph. It wasn't very mathematical. It wasn't very sophisticated. We just wanted to get a sense of the relationships or trade-offs of space and time, so to speak. And so on the x-axis or horizontal, we had the size of the problem. So like number of pages in the phone book or number of people in the phone book. And on the y-axis or vertical, we had the amount of time to solve the problem. How many seconds, how many page turns you could count using any unit of measure you like. And the first algorithm for Mike Smith, when I started with the very first page and turned and turned and turned, was a straight line, linear relationship. One more page, one more step. So it's straight line. The next algorithm was searching by twos, recall, in the first lecture. 2, 4, 6, 8. And that's still a straight line because there's a predictable relationship between number of pages and number of seconds or page turns. It's 2 to 1 instead of 1 to 1. So it's still a straight line, but it's lower on the graph. It's better. But the best one by far was the divide and conquer approach, we said, right? And it certainly felt faster. It's great because it was intuitive. It wasn't quite as easy to express in pseudocode. That was among the longer ones today. But it at least got us to the answer faster. And this is logarithmic in the sense that the logarithm, technically base 2 if you recall some of your math, it's because you're dividing the problem in half and half and half. And it's fine if you're uncomfortable with it, don't even remember what a logarithm is. For now, just assume that logarithmic time has this different shape to it. It grows much more slowly. Anytime you can choose log of n over n when picking between two algorithms, go with the log n or something like that, because it is going to be smaller, as we can see visually here. So let's just consider something like bubble sort. There's a couple of ways we can look at this. And again, the goal here is not to be very mathematical. We're not going to start doing proofs. But at least by taking a glance at some of the steps in this algorithm, you can get a general sense of how slow or how fast an algorithm is. And indeed, that's the goal. There's this fancy notation we're about to see called asymptotic notation with special Greek characters. But at the end of the day, we're really just trying to get an intuitive sense of how good or bad an algorithm is, much like we were trying to do with this picture. But now we'll do it a little more conventionally as a computer scientist might. So in bubble sort, recall that we compared every pair of humans and made a swap if they were out of order. And then we repeated, and we repeated, and repeated, and we kept going through the list. So that can be quantized. Like you can kind of break that down into some total number of steps. So if you've got n humans in front of the room and you want to compare them from left to right in pairs, how many possible pairs are there as I walk through the list for that first time? If there's n elements, and I can put the stands back where they were, how many pairs were there as I walk from left to right? I compared these two, these two, these two. Yeah, there's n minus 1, right? It's specifically 7. And even if you're not quite sure where we're going with this, if there's 8 stands, like this is 1, 2, 3, 4, 5, 6, 7, and there's 8 total, so that's indeed n minus 1. So that's how many comparisons we might have made the first time through bubble sort. But the very first time I went through the list in bubble sort, did the list get fully sorted? No, we had to do it again. We knew that 8 had bubbled up to the very end, so that was good. 8 was in the right place. But I had to do it again and fix more problems along the way. But the second time, I didn't need to go all the way through the list. To be clear, who did I not need to look at? The last location, or 8 in our very specific case. So the second time through the list of humans, I only have to make n minus 2 comparisons, right? Because I can just ignore number 8, the final human, and just deal with the 7 other humans that are somehow misordered. So if I wanted to really be nitpicky and write this down and count up how many steps or how many comparisons I made, we could kind of generalize it like this, right? It's going to be n minus 1 plus n minus 2 plus n minus 3 plus dot, 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 or more specifically, 7 plus 6 plus 5 plus 4. This is just a fancier formulaic way of saying the same thing. Now, I don't remember my back of math book formulas all that well, but I remember this one. You know, in your physics books or your math books, often in the hard covers, you'll see little cheat sheets for what series of numbers actually sum to or multiply out to. And so it turns out that that summation can actually be expressed more succinctly as n times n minus 1, all divided by 2. That is the same thing mathematically as the long series that I had a dot, dot, dot there for. So if I multiply this out, just using some algebra, that's like n squared minus n divided by 2. And then if I kind of multiply that out, that's n squared divided by 2 minus n over 2. So if I wanted to be really precise, this is the running time of bubble sort. It takes this many steps to sort n people. Why? Because I literally just counted the number of comparisons I made. That's how many comparisons it takes to do bubble sort. But honestly, this is really getting tedious, and my eyes are already starting to glaze over. I don't want to remember these algebraic formulas here. So let's actually try an example just to get a sense of how slow or how fast this is. Suppose that n were 1,000,000. So not 8, but 1,000,000 people or 1,000,000 numbers. How slow or fast is bubble sort going to be? Well, if we plug in 1,000,000, that's like saying n is 1,000,000. So that's 1,000,000 squared divided by 2. Minus 1,000,000 divided by 2, because that's what it all summed up to be. So if I do this out, it's a really big number, 500 billion minus 500,000. And in any other context, 500,000 is a pretty darn big number. But not so much when you subtract it from 500 billion, because you still get 499,999,500,000 after subtracting those off. Which is to say, of those two terms, the one on the left versus the one on the right, which is the bigger one, the more dominating factor in the mathematical expression? It's the one on the left, right? That's the one that's massively bigger. And so more generally, n squared divided by 2 feels like a bigger result than n divided by 2 alone. And we've seen it by proof by example, which is not a proof, but it at least gives us a feel for the size of the program or the number of comparisons we're actually making. So you know what? If that is the case, if the dominant factor, the one on the left in our case, the one with the square specifically, is just so much more influential on the number of comparisons we're going to make, then let's just wave our hands at the lower ordered terms, n divided by 2 and anything like that, and just say, this algorithm feels like n squared. I'm going to throw away the denominator. I'm going to throw away the thing I'm subtracting off. I'm going to throw away anything that is not the dominating factor, which is the term that contributes the most to the total number of steps incurred. And indeed, this is what a computer scientist would describe generally as the running time of this algorithm. It is on the order of n squared. It's not n squared, but it's on the order of n squared, as we've seen. It's pretty darn close, and that's good enough for a conversation with another reasonable person who wants to debate whether his or her algorithm is maybe better or worse than yours. So this would be called big O notation. Big O is used to refer to an upper bound on an algorithm's running time. Upper bound meaning, we'll consider, for our purposes, in the worst case, how much time might this algorithm take? Well, it's going to take on the order of n squared steps. Because if the list of numbers is unsorted initially, we got to do a lot of work to actually sort it. There's other terms that we could put in those parentheses. Some algorithms are not order of n squared. Some algorithms are actually order of n log n. Some algorithms are on the order of n itself, or log n, or even 1, where 1 refers to constant time. And in fact, the ones I've highlighted here, we've actually seen examples along the way of all of these so far. For instance, what algorithm have we seen that has a running time on the order of n steps? Linear search. If we think back even to today, to linear search, or from the first lecture when I was just looking for Mike really slowly, one phone book page at a time, that's a linear algorithm. If there's n pages or n humans, it might take me on the order of n steps because Mike Smith, S is toward the end of the alphabet, so he might be way over there or way toward the end of the phone book. Or God forbid his name starts with a Z, then I'm really going to have to go all the way to the end of the phone book. And so that's on the order of n steps. So n here would be linear. We've also seen another algorithm here in yellow, big O of log n. So just a moment ago, which of our algorithms was on the order of log n running time? Yeah, so binary search, divide and conquer. We didn't call it, we didn't describe it this formulaically in the first lecture, but that's how you would describe the running time, not just with a pretty picture, but just with an expression like this that all humans, at least computer scientists, can agree upon. And constant time. The funny thing here is because we're throwing away terms that don't really matter, O of 1 does not mean an algorithm that takes one step only. That would be a very limited number of options for your algorithms. But it does mean symbolically a constant number of steps. A constant number of steps. So what's something you might do that takes a constant number of steps in an algorithm? Maybe in like the first lecture, we had the silly peanut butter and jelly example. Which of the steps that day might have taken big O of 1 steps, a constant number of steps? I remember one like insert knife into jar. Like that's kind of one step. Maybe it's 2 because I might have to like pick up the knife and insert it into the jar then. 1 step, 2 steps, but it's a constant number. The number of steps is not at all informed by the algorithm itself. It just happens. You do that in 1 step. So there's any number of other algorithms here, and we'll leave in white one that we'll come back to. But let's just consider the opposite of this, if you will. If big O is our upper bound on running time, it turns out there's a vocabulary for discussing the lower bound on an algorithm's running time, which for our purposes we'll generally consider in the context of best case. So in the best case scenario, how little time might an algorithm take? Well, this is capital omega, and it's used in exactly the same way. You just say omega of n squared, or omega of n, or omega of log n. So it's the same symbology. It just refers to a lower bound. So it takes this few steps or this many steps. Big O, big omega. So what's an algorithm, therefore, that is in, so to speak, omega of 1? Like what algorithm, in the best case, might actually take just 1 step? And who is best to answer this question today in the room, in fact? What algorithm could take 1 step? Yeah. Yeah, linear search could take omega of 1 steps because in the best case, it is right there. Or in Chrissy's case, even if her algorithm is to sort of choose randomly, in the best case, it is right there, the number 50. So even her algorithm and even our linear search algorithm, and for that matter, even our binary search algorithm, are in omega of 1, at least in the best case, because if you get lucky, you're done, 1 step. By contrast, what is an algorithm that takes at least n steps? So omega of n. That's a good one. So you say bubble sort, I heard. Why?
Because if they're all already in order, you just go through each comparison and then make no swaps.
Good. So in the case of bubble sort, where we generally had a lot more work to do than just finding something with a searching algorithm, bubble sort is minimally in omega of n. You need at least on the order of n steps. Maybe it's n minus 1 or n minus 2, but it's on the order of n. Why? Because only once you go through the list at least once do you know what, to be clear? That they're in order. And you know that as a side effect of having not made any swaps. So you can only determine that a list is sorted in the first place by spending at least n steps on that process. Excellent. So there's yet another one, and this is the last, whereby if you happen to have an algorithm or a scenario where the upper bound and the lower bound are the same, turns out there's a symbol for that too. You can just describe the algorithm in terms of theta notation. That just means theta of n, theta of log n, whatever it is. That just means upper bound and lower bound are one and the same. And there's more formalities to this, and you can actually dive in deeper to this in a theory class, but for our purposes, big O and omega will be a generally useful way of describing, generally speaking, just what the running time of an algorithm actually is. So big O of n squared is the fastest we've seen thus far. Unfortunately, it does actually tend to run pretty slowly. We saw it with an example of like 500 billion steps just to sort a million elements. Turns out we can do way better than that, much like in the first lecture when I crazily proposed, I think, suppose your phone book had like 4 billion pages. Well, you only need 32 steps using binary search instead of 4 billion steps using linear search. So it would be nice if after all of this discussion of algorithms and introduction of these formalities, if we can actually do better. And it turns out that we can do better, but this has been a lot to do already. So let's go ahead in here and take a 5-minute break. And when we come back, we'll blow out of the water the performance of all 3 of those algorithms we just saw. All right. So let's take a quick look at what these algorithms look like so we can actually compare them against something that I claim is actually going to end up being better. OK, so here we have an array of numbers represented as vertical bars. So small bar is small number, tall bar is big number. And so it's a nice way to visualize what otherwise is pretty low-level numbers alone. I'm going to go ahead here and make the animation pretty fast. And I'm going to go ahead here and choose, for instance, bubble sort. And actually, let me slow it down a little bit, just for the sake of discussion. So you'll see in this algorithm, bubble sort, it's making multiple passes through the list, just as I did, highlighting in pink 2 neighbors at a time and deciding whether or not to swap them, just as we were with our 8 volunteers doing the exact same thing. Of course, with this visualization, we can do it more quickly, and we can speed this up to the point where you can kind of now start to feel the bubbling effect, if you will, whereby the bigger numbers are bubbling up to the top, to the right, just as the number 8 did when we did it on paper. So this is bubble sort. And we could watch this for quite some time. And in some sense, it's kind of mesmerizing. But in another sense, it's pretty underwhelming. Because at the end of the day, all you're going to get is a bunch of bars sorted from short bars to big bars. But perhaps the takeaway is that I'd kind of have to stall here for a decent amount of time, even though we're running this at the fastest speed, because it's only fixing, at best, one number at a time. And maybe some others are improving. But we're only moving all the way to the end, one number at a time. And we have to then go back and go back and go back and do more work. It's going to be very ungratifying to abort it, but let's go back to random. And now if we choose, for instance, selection sort, you'll see that the algorithm works a little differently. Let me slow it down. And what it's doing now, which is a little less obvious, is it's looking through the list for the next smallest element. And it's going to put it at the beginning of the list, all the way at the left. So it's looking and looking and looking, and it leaves highlighted in red the most recently discovered smallest element. And then as soon as it gets to the end of the list, it's going to move that smallest element all the way to the left, so that we now, kind of like the opposite of bubble sort, have all of the smallest elements to the left. Though this is arbitrary. We could bubble up the small elements by just reversing the order of our operations. We could sort from biggest to smallest. That is irrelevant. It's just by human convention, we tend to sort from smallest to biggest, at least in examples like this. And we can speed this up, but it doesn't quite have the same comparison effect, because all you're doing is a swoop through the list looking for the smallest, looking for the smallest, looking for the smallest. And so this way, it's going to kind of build up from short to tall. Let me go ahead and do it one more time, this time with insertion sort, and slow it down. And so what we're doing here is the following. We identify the next element, and then we go and insert it into the place it belongs in the quote-unquote sorted half of the list. So recall that I generally describe stuff on the left as being sorted, stuff on the right as being unsorted. And the implication of that is that even though these numbers here on the left are indeed sorted, when I encounter a new number out in the unsorted area, I might have to move some things around and shuffle things around. And unlike the cheat I was doing here in person, when I grabbed that music stand before and just kind of moved it over here, that's not really legitimate, right? This is garbage value land. Like, I should not have had access to this memory. And so what we did with our actual 8 humans was more legitimate. The fact that our volunteers did the physical labor of moving those numbers around, that was the low-level work that the computer has to do too. And you see it here all the more, either at this slow speed or the faster speed. It's being inserted into the appropriate location. So case in point, this tiny little element, we have to do a huge amount of work to find its location until finally we found it, and now we do the same thing. So all of these have some pluses and some minuses. But it turns out with merge sort, we can do even better. An algorithm that goes by the name of merge sort. But to do better, we need to have a new ingredient, or at least more formally defined, that we've kind of sort of leveraged before, but not by name. And to do this, I'm going to actually take out a little bit of code in CS50 IDE, a program called sigma0.c. And we'll see the interconnection in just a moment. So in this program, notice the following. We have a main function whose purpose in life is to get a positive integer from the user, and to pester him or her again and again and again until they cooperate and provide a positive integer. That's what the do-while loop is often useful for. And then what do we do with it? We simply pass that value n that the human typed in via getInt to a function called sigma. And sigma is like the Greek character, the capital E-looking character that generally means in math like sum a bunch of numbers, add a bunch of numbers together. So this is essentially a function called sigma whose purpose in life is to sum all of the numbers from 0 to n, or equivalently from 1 to n. So 1 plus 2 plus 3 plus 4 plus ... n, whatever n happens to be. And then via printf, we're just printing it out. So let me just run this program to make super clear what's going on. And I can do this by doing, of course, in my source3 directory for today, make sigma 0, enter, /sigma 0. Positive integer, I will do 2. So by that definition, it should sum 0 plus 1 plus 2. So 1 plus 2, that should be 3. So I should see 3. And indeed, I see 3. Let's do one more. If I add in 3 numbers, so this should be 1 plus 2 plus 3. So that's 6 in total, and so forth. And they get pretty big pretty quickly. If I do 50, then we start to get into the thousands. So that's all it's doing. And how is it doing this? Well, we could implement this in a whole bunch of ways. But if we leverage some of our sort of techniques thus far, we might do it using a for loop. That's kind of been one of the most common tools in our toolkit. And how am I using it here? Well, I'm first declaring a variable called sum and initializing it to 0 because I've done no work yet. Then I have a for loop for I equals 1 all the way up through m. Why m? Well, just because. Recall that when you make your own function, whether in Scratch or in C, you get to decide what to call the inputs to that function, the arguments or parameters as they're called. And just for clarity, I called it m, even though we've typically been using n. I could have called it anything I want. I just wanted to make super clear it's a different variable, but more on that in a week or so. And so I'm just counting from 1 to m, and I'm adding to sum whatever I is. Now, just as a quick check, why am I not doing sum plus plus, as I usually do in these kinds of cases? Exactly. I'm not incrementing by 1. I'm incrementing by 1, and then by 2, and then by 3, and then by 4, and so forth. So I need this loop to be counting up, and I need to be adding I to the sum, not just a plus plus in this case. Then I return the sum. And so this is an example of like an abstraction. Like I now have a function called sigma. Just like in math, you might have the big capital sigma symbol that just says add all these numbers together. I have a C function that does that. And so now higher up in my code, I can call that function and then print out the answer. But it turns out that this simple function lends itself to a nice example of another programming technique, something called recursion. And we won't have terribly many opportunities in CS50 to apply this technique, though we will towards semester's end. If you continue on to a class like CS51, you'll use it all the time. If you use another type of programming language, you'll very often use this technique. And it's called recursion, and it looks like this. Let me go ahead and open up another file that's available on the course's website called sigma1. Notice that main is identical. So main is identical, and indeed it's still calling a function called sigma and then using printf to print out the answer. So there's no difference there. But what is different in this next version is the code for sigma. So what's going on here? It still takes as input an integer called m. So that's good, because I need to know what to sum up to. It returns an integer as before. And it amazingly has like 4 real lines of code plus some curly braces, and even those lines of code are super short. And there's no additional variables, and there's this weird, crazy logic here. But let's see what it's doing first and foremost. On line 23, I'm saying if m is less than or equal to 0, return 0. Now, why does this make sense? Well, I only want to support positive numbers or non-negative numbers from 0 to m. And so I just kind of need an error check there, right? If the human somehow passes into this function -50 or something else, I don't want the function to freak out and give unpredictable behavior. I just want it to return 0 in cases of error or when the number gets that small as to hit 0 or even lower. So this I'm going to call a base case. It's just like this sanity check, like don't let the math go beyond this point of 0 or less. So amazingly, if you really zoom in on this code, the entirety of this program really boils down to one line. And what's going on here? So I am returning from sigma an answer. But curiously, my answer is kind of defined in terms of itself, which generally is a bad idea, right? It's like in English, if you try to define a word by using the word in the definition, usually someone calls you on that, because it's not all that helpful to use a word in the definition of the word. And that's the same idea at first glance of recursion. You are using the same function to solve a problem that was supposed to be solved by that function in the first place. So what do I mean by that? Main, of course, is calling sigma, and that means this code down here that we've been looking at gets executed. So suppose that we hit this line of code. What recursion allows us to do in this case is take a bite out of the problem and then defer to someone else to figure out the rest of the problem. So what do we mean by that? Well, sigma, again, is just this process of adding up all the numbers between 0 and some number m. So 1 plus 2 plus 3 plus ... So you know what? I don't want to do all that work as I did in version 0 with my for loop. Let me just do a piece of that work. And how do I do that? Well, you know what? When you ask me, what is the sum from 0 to m, I'm going to be kind of circular about it and be like, well, it's the answer is m, the biggest number you handed me, plus the sum of everything below it. Right? So if you passed in the number 10, it's like saying, well, sigma of 10 is 10 plus sigma of 9, and like, leave me alone. I don't want to do the rest of the math. But because you're calling the same function again, that's actually OK. A function can call itself. Because if you think about where the story is going, now sigma gets called in this story with sigma of 9. What does the code do? Well, sigma of 9 returns 9 plus whatever sigma of 8 is. So we're not solving the whole problem. We're handing back a 10 plus a 9, and if we keep going, plus an 8, plus a 7, plus a 6. But we're not going to do this forever. Even though I'm using sigma in my implementation of my answer, under what circumstances am I not calling sigma? If m equals 0 or is even less than 0, which shouldn't happen, but just to be sure, I made sure it can't with the less than or equal to. So eventually, you're going to ask me, what is sigma of 0? And I'm not going to be kind of difficult about it. I'm just going to say 0. And no longer do I keep passing the buck to that same function. And so even though it takes a while to get to that point in the story, because we say 10 plus sigma of 9. Sigma of 9 is 9 plus sigma of 8, which is sigma of 8, or 8 plus sigma of 7. Like, it keeps going and going and going. But if you kind of mentally buffer, so to speak, much like a video in your browser, all of those numbers that you're being handed back one at a time, which are technically being added together for you by your program with the plus operator, the last number you're going to be handed back is 0. And at that point, all of the plus signs can kind of kick in and give you back whatever number you're actually looking for. So recursion is the act of a function calling itself, which is very, very, very bad unless you have a base case that ensures that eventually, as you take bytes out of the problem, you will handle, with a special case, so to speak, a base case, a small piece of the puzzle, and just hand back a hard-coded answer to make sure that this doesn't happen infinitely many times. So any questions on this principle of a function being able to call itself? Yeah?
So the base case here was when m equals 0?
When m equals 0 or is even less than 0, just to be sure. But yes, when m equals 0. Indeed. So let's see. If you're comfortable at least with the fact, oh, and actually there's a good little geek humor now. If you go to google.com, and suppose you're wondering what recursion is, especially a few hours from now, well, you can Google it. And then the computer scientists at Google, there we go. OK, so if you're laughing, you get it, which is great. So that then is recursion, something giving you back an answer in terms of itself. So why is this useful? Well, it turns out we can leverage this now to solve a problem if we know that we can actually convert it to code. We'll focus less on the actual implementation and more on the idea. But let's see if we can't wrap our minds around the problem to be solved with this code. This is merge sort in pseudocode. And again, like all the pseudocode we've ever written, you could write this in bunches of different ways. Here's one such way. Notice the first thing on input of n elements, so n numbers, n blue books, and whatever, go ahead and do the following. If n is less than 2, return. So it's a little different from the condition I had a moment ago, but the context here is sorting. It's not summing. So why is it logically OK to say if n is less than 2, just return? Yeah, that's just itself. If it's less than 2, that means there's only one blue book, or maybe even 0. So in either case, there's no work to be done. Just return. The list is sorted, however short it is. But if it's longer than that, you might have to do some work and actually do some actual sorting. So what happens then? So else, you know what? Sort the left half of the elements, and then sort the right half of the elements, and then, OK, merge them together. So it's this same kind of like blasé attitude where, like if you ask me to sort something, I'm just going to tell you, well, you go sort the left, then you go sort the right, and then we'll just merge the results back together. And this is cyclical in the sense that how do you sort the left half of anything? You need a sorting algorithm. But this is the sorting algorithm. So this is like saying use merge sort to sort the left half. use merge sort to sort the right half, and then merge them together. Merging doesn't really need to be a fancy algorithm. Merging is like if you've got one pile of numbers here that are sorted, one pile of numbers here that's sorted, you can just kind of eyeball them and grab the appropriate one to kind of interleave them in the right order. That's what we mean by merging. So how in the world is this even correct? Because we haven't actually done any apparent work in this way. There's no loops. There's no comparisons, it seems. It's just completely recursively defined, so to speak. Well, let's see what actually this means. And this is a sequence of visualizations that can you can potentially fall off the story of. So I'll try to go slowly, but not so slowly that the example itself is boring. We'll just go through this once. And then again, the slides are online if you kind of want to step through the visualization. So here is a list of 8 numbers, the same 8 numbers that we looked at before. I've drawn them in contiguously as though they are in an array. This list is currently of size 8. So an input of 8 elements is the beginning of this story. What was the first step in our algorithm? Well, we were going to check if n is less than 2, return. That is irrelevant because n is 8, not less than 2. So that's a moot point. So the first 3 things for me to do to sort this list is to sort the left half, then sort the right half, then to merge the sorted halves. OK, so let's see how we get there. So here's the list. Here is the left half. And I need to sort the left half, apparently. How do I do that? Well, how do you sort a list of 4 elements? Break it up again. Sort the left half, then its right half, then merge those 2 halves together. So let me do that. I'm going to draw a box around only the elements we're thinking about at the moment. So let me look at the left half. OK, now I need to sort this list. How do I sort a list of size 2? It's actually 2. It's not less than 2, so I have to do some work. So how do you sort a list of size 2? It's a little strange to say it, but sort the left half, then sort the right half, then merge the 2. And at this point in the story, you may very well be lost because we literally just keep saying the same thing and not actually doing any work. But think of it like you're buffering these instructions. Like I've said to sort the left half, then the right half, but you focused on just the left half for now. But unfortunately, you got a little distracted because now to sort the left half, you have to sort the left half, so you have to do a little more work. So if you just kind of let this mental baggage build up, we have to remember to go back through it. But we've not actually done the real work yet. We're about to now. Because now that you've told me, given a list of size 2, sort the left half, here's where we bottom out with that base case and actually start to make some progress. So here's 4 and 2, a list of size 2. Let's sort the left half. How do you sort a list of size 1? You don't, right? Because n is 1. 1, of course, is less than 2. And what was the one instruction we had at the top of this function merge sort? Just return, like do nothing. So OK, everyone, I have now sorted the number 4 for you. Like, it's true. It's kind of a foolish statement. But the magic must therefore come when we combine the results. So let's see where the story goes. I've sorted the left half. Done. Return. Now, what was I supposed to do next? Now I have to sort the right half of that list of size 2. OK, done. What's the third step at this point in the story? Merge them. So I'm now looking at a list of size 2 again, each of whose halves is sorted, according to the crazy logic we're using here. But now something interesting happens. I have on the left the number 4. I have on the right the number 2. And each of these lists is of size 1. And if you in your mind's eye or just visually with my fingers, consider like your left hand pointing at the first list, your right hand pointing at the second list, the process of merging numbers is just comparing what your fingers are pointing at and deciding which one comes first. Obviously, 2 is going to come first. So in a moment, we'll see that 2 should move over here. And then there's nothing left for my right hand. It's done. So 4 is obviously going to go here. And that process of merging 2 followed by 4 is what we mean by merging. It's pretty much what I was doing with insertion sort. But here, we're just doing it with individual elements at a time, kind of weaving things together or zipping things together with like a zipper, if you think of it that way. So now let me grab 2 and put it here. Let me grab 4 and put it here. OK, so I sorted left half. I sorted right half. I merged them. How do we unwind the story? Where did we leave off? Now we have to sort the right half that was like a minute ago in the story, which, just to highlight it now, is the 7 and 5. So now I have to do the same thing. I'm sorting a list of size 2 that happens to be on the right of the left. So now I sort the left half. Done. Sort the right half. Done. I now have to merge the 2 together. So now my hands have to do some work, but I'll just do it from over here. 5 goes down, then 7 goes down. And at this point in the story, we have sorted the left half of the left half and the right half of the left half. So what point in the story are we at now? All right, we have to, well, we did the right half just now. We now have to merge the two halves together. And frankly, if you do this at home, if you want to kind of retrace your steps, literally just write down a to-do list, like from top to bottom on the sheet of paper. And then as you do something, cross it off and go back to the previous thing in the list. You would actually see or feel even more what it was, that mental baggage you were accumulating that you need to tend to. But now I have two lists of size 2. So let's do the finger thing again here. So I start pointing at the left list, start pointing at the right list. The first number to merge in is presumably going to be 2. Then what comes after that? I'm going to update my left finger. So now my left hand's pointing at the 4 at this point. My right hand's still pointing at the 5. So which comes next? 4. There's no more work for my left hand, so it's probably going to be pretty trivial, 5 and 7. But I do need to do the merging. It looks merged already, but we have to do it. And I'm going to do it in some new space just as before. So 2 and 4 and 5 and 7. And now you can really see it for the first time. The left half of the original list is finally sorted. Unfortunately, like 3 minutes ago is when we started this story, and now we need to unwind in our mind to go back to the original right half. So if you think about it now, even though I've said a lot of words, this is technically the second step in our algorithm, or at least the first invocation thereof. All right, so we'll do it a little faster, but same idea. Sort the left half. How do I do that? Sort the left half, then the right half, which are stupidly easy and done, but now I have to merge 6 and 8. So merging in this case didn't have much effect, but it needed to be done to be sure. Next, let's sort the right half of the right half. Now I'm going to sort the left, sort the right. Now the key step is merging, and now we're doing some actual work. And now we really have some work to be done. Now we have to sort the left half and the right half of the original right half. So it's 1, then 3, then 6, then 8. Now we're finally almost at the end. Now what do we do with these? Now we have two halves, the original left and the original right. And you can think of the fingers as doing the work again. 1's going to go here. 2's going to go here. 3's going to go here. Then 4. And I constantly compare where my fingers are pointing. But my fingers are constantly moving from left to right. As soon as I deal with a number, it advances to the next number in the list. So it's obviously going to be now 1, 2, 3, 4, 5, 6. But notice, if you imagine my fingers doing this work, they're constantly moving toward the right to the end of the list. So as soon as my fingers hit the ends of those lists, I must be done merging. And voila, we've now sorted the elements. It's a huge number of words, and it would be a nightmare to kind of do it with humans because there's just so much going on, and you have to remember or buffer so many of those steps. But in the end, we've done something that is kind of captured even by this picture. So it turns out that merge sort, even though it sounds like a long story, is fundamentally faster. And it's fundamentally faster because we're dividing the problem in half, as we have been doing with binary search in the phone book example even days ago. So if we look on the screen, you can kind of see the sort of the remnants of work that we've done. Like how many times did we move the elements from one row to another? They started up here. Then they eventually made their way here, and then here, and then here. So that's 1, 2, 3 movements of the letters, or of the numbers in memory, if you will. So if you imagine each of these rows is just a different chunk of memory and RAM, I'm just moving things around in memory. So 3 is just a number, but it turns out, and if we did more general cases of this, turns out that log base 2 of n, where n is 8 is the number of elements we started with, log base 2 of 8 is 3. And so indeed, and if you'll take on faith for now so that we don't have to go through an even bigger example to show it even more, the number of times we move the numbers is going to equal, it turns out, log base 2 of n, which in this case happens to be 3. And so that then invites the question, on each of the rows, every time you move these numbers into a new location in memory, how many times are you touching that number while it's in that position? Or how many times equivalently are you looking at it to do something about it? What do I mean by this? Well, the movement from top to bottom was happening anytime we did the merging, right? We would move the numbers from here to here. But as soon as we did that, we had to do some work with the left pointer and right pointer. I needed to then merge those together. And I emphasized earlier that anytime I'm comparing numbers, my left hand and right hand are constantly advancing from left and right. I never double back, much like I constantly was doubling back with bubble sort, insertion sort, selection sort. There was so much damn comparison going on. It felt like a lot of work, and it physically was. But here, merging, I'm moving things around, but my hands are constantly moving forward. looking at, on each row, n numbers total. My left hand or right hand pointed at each of the numbers once. Never doubled back. So it was never n plus 1 or 2n. It was just n. So we have log n movements of the numbers in memory. And every time we do that, we merge them from left to right effectively, touching each number once. So we're doing n things log n times. And so that would be mathematically equal to n log n. So again, even if you're not super comfy with logarithms, you do know from our picture with the straight lines and the curved line that which is smaller, log of n or n, generally speaking? Like log of n is smaller, right? That's why the green line was lower and it was also curved. It was below the linear line n. So generally speaking, the bigger n gets, the more slowly log n grows. And again, if just take on faith that this is a mathematical expression that communicates the time required to do something, it's less. So which therefore is smaller? N squared, which of course is n times n, or n log n? N log n. So we've now found an algorithm that's unlike all of the others we've seen. And even though it took a while to explain, and even though, frankly, you might have to kind of sift through it again to really wrap your mind around it, it took me a while too, it is fundamentally faster as well. So just to take one other stab at this, let me show one other perspective, at least if you're more mathematically comfortable. And after today, if you're worried that this is way more math than you were expecting, realize we very quickly abstract away from these details and we start to wave our hands using big O and big omega. Let's consider how we could look at this a different way. If the picture wasn't really working for you, let's see if we can just like jot down how many steps each of these lines of code is. And there's not many lines of code here, so it shouldn't be a very long expression. So how long does it take to decide if n is less than 2? And if so, return. Well, you're past a bunch of numbers, so I'm going to call it constant time. Like you know how many numbers you've been handed. Nope, it's not less than 2, or yes, it is. You're just answering yes or no. Constant time, big O of 1. All right, so I'm going to describe that as this. This is the formal way of saying it. T of n, which is just how much time does it take given a problem of size n. Just a fancy way of saying that. It's on the order of 1 step. Maybe it's 2, maybe it's 3, because you kind of got to look at something. But it's a fixed number of steps to decide there are fewer than n elements in front of me. It's not going to take you very long. So that piece of the puzzle takes big O of 1 step. So now we have 3 other questions to ask. That's like kind of a throwaway. That's really quick if it's just 1 step or 2 steps or 3 steps. So are these the expensive things? Well, let's see. Sort the left half of elements. Well, here too, I can be kind of clever and propose the following. You know what? The amount of time required to sort n elements is technically equal to the amount of time it takes to sort half of those elements, plus the amount of time required to sort the other half of those elements, plus, to be fair, some merging time. And it's essentially n, but I'm going to generalize it as big O of n, because I did have to move my hands around. But again, the key thing was my hands were constantly moving to the right. There was no looping back and again like with the other algorithms. So it's like n steps to do the merging. If I've got 4 numbers here, 4 numbers here, I have to touch a total of 8 elements. 8 is n, so it feels like, yes, on the order of n steps to do the merging. Unfortunately, this is like a recursive answer to the question of how efficient is merge sort. But that's kind of consistent with the fact that merge sort is being implemented recursively in this code. And it turns out here too, if you've got one of those old school textbooks that's got a cheat sheet in the front or the back of your physics or your math book, this is a series that you can actually, that mathematicians know, actually sum up to something known, which is n times log n. And we won't go into the weeds of why that is mathematically, but if you take a problem of size n and add the running time for first half, second half, and then add an n, this is what mathematically it ends up being. And so if you're more comfortable with that, realize that this derives from just counting up of those several steps. And ultimately, this is much better than that. And in fact, we can kind of feel this here. You'll be able to feel it's even better with other data sets. But let me go ahead and reload here and go ahead at the same speed as we were before, choosing merge sort. Let me fit it onto the screen at once. Actually, I should speed it up to the original. So what is it doing? It's using a bit of extra memory, just as we were on the screen, using some additional space. But notice as it does that work, It's kind of moving things back and forth. And it's actually saving space. Even though I used log n amount of memory by keep moving it, this was stupid. Like, I didn't need to keep using more memory, because I wasn't using the stuff anymore above. So with merge sort, you really just need twice as much memory as those other algorithms, because the first time you need to move them here. And then, even though I did it visually, deliberately to move it to yet another location, just keep moving things back and forth as needed. And that's what's happening with that algorithm there. It's not quite as clear to see with this visualization. So let me open up this other one here. Now go. And you'll see merge sort all the way on the right. Done. All right, so insertion sort got a little lucky here just because of the order of the elements and the size of the data set isn't that big, which is why I wanted to show the other one. But if we do it once more, you'll see again that merge sort is pretty darn quick. And you can see it doing things in halves. And selection sort and bubble sort are still doing their thing. And if we did this using not like, what is that, 10, 20 bars total, but 100 bars or 1,000,000 bars, you would really, really feel the difference, just as we did with the phone book example as well. Any questions there on that? And we won't walk through the code, but if you're curious to actually see how some of these ideas map to C code, you will find in the CS50 appliance in the source code from today a couple of files, binary 0 and binary 1 and linear.c, all of which implement binary search and linear search in a couple of different ways if you actually want to see how those map. But what we thought we would do in our remaining time today is tee up one of the next algorithmic challenges. It turns out that there are wonderful opportunities in computer science to intersect with other fields, among them the arts and very specifically music. And it turns out that music, whether you're an audiophile or even a musical theoretician, there are relationships among the sounds that we hear and the rate at which we hear those notes, which is to say they follow patterns. And these patterns can be produced by computers. They can be generated by computers. And what we'll do ultimately in problem set 3, in fact, is introduce you to a bit of the musical world, whether you have some prior experience or not. And Brian, if you wouldn't mind coming up just to assist with this teaser. Here are just a few keys from a keyboard, and here are 88 keys from an actual keyboard. And Brian will help us in just a moment with some of these definitions. But you'll see here that there are 8 keys, or 1, 2, 3, 4, 5, 6, 7 white keys, and 5 black keys on the board. And it turns out that mankind, at least in Western music years ago, decided to standardize on how we describe these keys. And we assigned letters to them. And you might have heard of middle C, even if you've never played a piano before. And you might think of that as being the leftmost key there. And then it's D, E, F, G, and then A, B. And of course, on a real piano, there's keys to the left, and there's keys to the right. Do you want to play what C might sound like here? So that's C. And then if you want to, very well done. Do you want to go all the way up through the scale to B? Sure. It's kind of unresolved too, because what should have come next? That would be another C. And so what Brian's played for us is a full octave now, referring to 8, so C to C inclusive in this case. And those of us who kind of are familiar with music or like listening to certain music, you'll notice that certain things sound good, and there's actually mathematical and formulaic or algorithmic reasons that some of these sounds sound actually good. But what about these black keys? They are actually can be defined in a couple of different ways. And if you've ever heard of flats or sharps, Brian, do you want to explain what the relationship now is among the white keys and the black keys and how they sound different?
Yeah, sure. So a bit of terminology first. A semitone is just the distance from one note to the note immediately after that, both white and black notes included. And all it means for something to be sharp, represented by the hashtag or pound sign up there, is take a note and move it up by 1 semitone. So if we start with C and make that note sharp to C sharp, we move 1 semitone to the note immediately after it, which is that black note in between C and D. So that's C sharp. And likewise, if we add E sharp, that is 1 semitone or the note immediately after E, which in this case is the same thing as F. So F and E sharp are the same note. And in the meantime, flat is just the opposite of that. If sharp means move up 1 semitone, flat means move down 1 semitone. So if I have E, E flat is 1 semitone moving left on the piano keyboard.
And so even though a typical piano keyboard wouldn't be labeled as such, it does follow a pattern, and it does repeat to the left and to the right as well. And so as you learn to play piano, you learn what these notes sound like. You learn where these keys are. And you also learn, ultimately, how to read music, which might look like this. This is a familiar song, now officially in the public domain. And you'll see here that there are these little shapes called notes, or little circles, that happen to be on specific lines. And it turns out that if a note is on one line, it might represent the note A. If it's on a different line, higher above or down below, it might represent B or C or D or E or F or G. And if there's a sharp symbol or a flat symbol in front of it, that might off-shift it ever so slightly so that you're actually touching, in many cases, one of the black keys as well. Which is to say that once you have the vocabulary and you know what the alphabet is to which you have access, can you start to write it out, much like we write computer programs, but this is what a musician would actually see. And just to give us maybe a teaser of what you can actually do when you take into account the different sounds of notes and the different pace at which you play notes, can you give us a little something more than just a scale?
Sure.
So if you're a little worried what we're getting into, not only computer science and programming, but now music, I am absolutely among the least comfortable with this. And this is why Brian has kindly joined us here today. But it'll be fun, we hope, ultimately, to explore these relationships and also the intersection of one field with another. And to now tie these topics together, we thought we'd end by looking at a short visualization here, about a minute's worth of computer-generated sounds that give you not just a visual feel of some of the algorithms and others that we've looked at today, but also associate sounds with the operations of moving things, swapping things, and ultimately touching bigger and smaller numbers digitally. So here we have up first, insertion sort. Again, it's inserting into the right place the number. This now is bubble sort. And again, you can both see and now kind of feel all of the swaps that it's doing. We will get the satisfaction this time. This now is selection sort, whereby you go through the list selecting the next smallest element and plop it in its place. And the bars are getting higher and higher, just like the notes or the frequencies. This now is merge sort. And notice the halves that are developing. And this is by far the most gratifying sound at the end of this one. This is gnome sort, which we didn't look at, but very distinctly has a different shape too. It's not quite as ordered as the others. And that then are algorithms. And Brian will play us out for today. Otherwise, we will see you next week.